So there are no poles. There are no points in which or singularity in which the algebra is not well defined. So at this point, I can define convergence by interchanging the two. So,
and this sequence required to be Cauchy sequence?
If it is a Cauchy sequence, yes. So, if it's any this is a convergence in the sense of complex numbers, so a Cauchy sequence in the sense of see, in order to give a topology on a set of points, I can do two things. Either I can say the set of open sets, or equivalently, I can give the definition of convergence of points. This gives me a topology, no? Because a point will belong to the neighborhood if sequences go converging and so on. So I use topology in the sense of convergence of the sequences. Okay, and this gives me the way in which I can define not only the points are the states, the pure states. And this gives me a way of definition of the convergence of pure states, sequence of pure state to a limiting pure state. And I do it by using the evaluation map for all functions. Okay? So, the important thing, the philosophical important thing is that there is a, let me say if I wrote something which I didn't say. Okay, so at this point, the starting algebra is the algebra of continuous functions over the set of states which are the points. So the set of states construct the topological space. And I could do the same in set of ideal, and the two topology are the same for the commutative case. As I said, you see the philosophy, however, is that instead of looking at the points, I look at the points as states, because the states exist also for non-commutative algebras, while the points exist only for commutative algebras. So commutative algebra is always the algebra of continuous functions over a set of points. But I can have non-commutative algebra, but still have the states. They will not be points, but they will be the states. Now, and this is a very nice thing, for especially if you do quantum mechanics, because the algebra are operators. So I define you the algebra in an abstract way. The properties, so I can sum, I can multiply, and I have a norm. But there is, I want to do everything with a spectral point of view. Spectral means spectrum of operators. And I can do this because ABC star algebra is always representable as bounded operator on an Hilbert space. So the Hilbert space is there. It appears, but it's not the algebra. It's this. I can represent the algebra there, and I can, and the construction is the Gelfand-Naimark-Siegel construction. And I will quickly show this without detail. Every algebra has an action on itself, no? Because there is a representation of the algebra on itself, because I can multiply two elements of the algebra. And consider the algebra as a vector space for the construction of the inverse space. Okay? What we need is an inner product with certain properties, and then we need to complete in this other norm. Okay? We need, because the inverse space also is complete. Okay, now, if I have a state, this gives me a bilinear map, because if I say I have a state phi, and I have two elements of the algebra, I can define what will be an inner product. It's not yet an inner product. For the moment, it's a bilinear map in this simple way. Now, this has the property of the inner product, except that there are some elements in the algebra for which this is 0, phi of a dagger A is 0, even if A is not the null vector. And this is a requirement for the inner product. So what do? I can these states form a left ideal. An ideal, I have to say what an ideal is. An ideal is a subalgebra of the algebra, such that if I have an element, so an ideal is such that if B belongs to the ideal, A times B belongs to the ideal for any element of the algebra. Subalgebra tells that the product of two elements belongs to the subalgebra for two elements of the subalgebra. This is bigger, even if you get out of the subalgebra, somehow multiplying it calls it inside the subalgebra, and this set of states form this set of elements of the algebra for a particular state form an ideal, and this can be proven as an exercise, and one can quotient out this ideal. So I take as a vector space the set of equivalence class of the algebra divided by this idea. This scalar product now is well defined, that it is independent, there is an exercise on the representatives of A and B in the equivalence class. So I take the equivalence classes of the algebra modulo an element of the ideal, but the element of the ideal will give 0 in this inner product. So this inner product is independent of the elements of the algebra, and so this is a good definition. So this is a Hilbert space. Now I have a scalar product which defines a good norm. The Hilbert space is not yet, because I have to complete in the scalar product norm, for which A acts in a natural way as bounded operators. And one can do the GNS construction for matrices, starting for a pure state, and instead I take the continuous functions over the line, can be also any other manifold. Now consider these two states. One is the evaluation map, okay, and one is the Hilbert. This is a space. No, this is not a pure state. I can. This is a state because it has all the properties. I take an element and I get a number. This will make it converge the integral for sure. So those two are states. This is a pure state. This is not. And one has to find the Hilbert spaces in the two cases. And this exercise actually I will do later on because it's instructive. Okay, now let's go to non-commutative spaces. So this is really the philosophy, is that I have an algebra. The algebra is commutative, it corresponds to a space as I know it. But I can describe things, and I will see even more things that I can describe in an operatorial way. So I can do everything in operators on Hilbert spaces. Now, I can generalize to non-commutative spaces, or to also fake non-commutative spaces. I'll show you what I mean. So I have a correspondence between Hausdorff space and non-commutative sister and commutative sister algebra, and I can ask what happens for non-commutative sister algebra. Now, it's still possible to give topology on the space of irreducible representation, pure state and maximal or primitive ideal, but they don't coincide anymore. Okay, these three topologies don't coincide. For us, a non-commutative space will be, by extension of the concept, a non-commutative sister algebra. Because, so what is the rationale? A commutative sister algebra is a commutative Hausdorff space. Commutative, I say commutative, but it's a normal space, no? Normal in English, not mathematical sense. State made of points. So for me, a non-commutative space will be an algebra. There may be points or there may not be points. There may be something which looks like points, coherent states, or they may not be nothing at all. But for me, a non-commutative algebra C star, it's a space. It's a non-commutative space. However, sometimes it's possible to talk of points, perhaps generalized, and sometimes it doesn't make any sense. For example, P and Q of quantum mechanics. This is a deformation of ordinary algebra function of phase space. Pure states are what? Are square integral functions on R. So my space is R2, but the L2 is L2 of R, either position or momentum, or any other basis, of course. Another good thing is that all Hilbert spaces are the same. They are isomorphic. It's all separate Hilbert spaces are the same. So pure states are square integral functions, and there are no correspondences with the original points. Okay? Yet there is something which looks like the original points, and those are the coherent states. Okay? But they are not all the set of pure states. There are particular subsets, and so physically we recognize them, but mathematically there has been a big difference. Now, however, there are some more trivial cases. Take the example of matrix-valued functions on R. So take functions on the line with values in 2 by 2 is sufficient. Nothing changes from 2 by 2 to compact, nothing changes. The algebra is non-commutative, but obviously there is an underlying space, which is R itself. So, okay, in order to capture the fact that I might have a non-commutative space which is actually commutative in the sense that there is something underneath, I need the concept of Morita equivalence. In order to do that, I need first the concept of Hilbert module. This is a generalization of Hilbert spaces where the field C is replaced by a C-star algebra. So a right Hilbert module E over A is a right module equipped with a sesquilinear, I love to say sesquilinear form. It's just like the inner product properties. So which means that if I multiply two elements with an A with this inner product, sesquilinear form, then A I can take out. So A belongs to the algebra, eta belongs to the Hilbert module, and there are all these properties. They are true for Hilbert space if A is a complex number. I'm just generalizing. Okay, so instead of if the algebra is complex number, I would call this an Hilbert space, and then I complete in the norm. And this is a right Hilbert module, and I can define a left one. And I can take the algebra of matrices and I can make it into a module, and I can discuss the automorphisms. And two C-star algebra, A and B, are said to be Morita equivalent if there exists a full Hilbert Hilbert A module, which is the same, which is at the same time a left module for one and a right module for the other one. So a right for A and a left for B, and these structures are compatible. Okay? This tells me, and I will do the exercises if there is time, this tells me that this the algebra of complex number, matrices of any rank over the complex, or even compact operators, which are infinite matrices, but a particular kind of infinite matrices. They are all Morita equivalent. And the two Morita equivalent algebras have the same space of representations, so they describe the same non-commutative space. So for me, when two algebras are Morita equivalent, from the point of view of which geometry, commutative or non-commutative, they are the same. In particular, of course, if an algebra is non-commutative, is Morita equivalent to a commutative one, then I have the points. I have the point of the commutative one. It will be in general the algebra of matrices or operators, of functions with values in matrices or this line.
So can I look at some algebra and decide whether there is some Morita equivalent commutative algebra?
The information is there. Whether you are able to extract it, I don't know. You have to be smart. So the information is there, but is this, the information is there.
But for matrix algebra, there is.
For matrix algebra, it's trivial. Yes, but if you come with a complicated algebra and you ask, there are lots of notions of amenability. So there are ways in which you may say if they are Morita equivalent or not. So there are some cases in which you can say that it's not Morita equivalent to a commutative algebra. But if I come with a very complicated example, although the information is there, a human may not be able to see it. But the information is there. There is no ambiguity. Whether you are smart enough to recognize which one is the algebra or that there is no algebra, then
there is a standard recipe for that.
There is not an algorithm that you can do. Pretty much, yeah, in fact, I asked the support of the mathematicians. There is no, but is there, in the eyes of God, everything is well defined. It's us that may not be able to solve the problem. It's like, if you have the data of a Cauchy problem over a Cauchy surface, you can propagate to the whole space, but that doesn't mean that you are able to write the equation that propagates any partial differential equation, something like that.
Sometimes that they are not with the equivalent can be seen to see if they are different K theories.
Yes. Yes.
For example.
Yes. K theory.
Well, there was a tool for
Yes.
spaces. So if the two algebras are Morita equivalent, then their K theories are the same. Converse is not
Yes.
so you can distinguish. These some two spaces have same K theory. That would mean that different K theory. That would mean they are not.
Yes. So K theory, for example, it's
one way.
Yes.
Can help you. Something like that.
so that's, for example, yeah, you know that non-commutative torus will certainly not be for an irrational Morita equivalent to something that so the negative is always simpler somehow. But also there are cases in which they may have the same K theory of an equivalent, but that doesn't. Fortunately, we use matrix. For matrices, we know what is the Morita equivalent. They are all equivalent. For matrices, they are all equivalent. Okay, metric. So now let me introduce one of the main ingredients of the condition of non-commutative geometry. And I have the algebra. The algebra acts on as bounded operators on the Hilbert space. And I introduce a self-adjoint operator on the Hilbert space with compact resolvent. And this can be seen as a generalization of the Dirac operator. And sometimes will be the Dirac operator. And sometimes will look completely different. I will often call it the Dirac operator. Sometimes it will be completely different than the one introduced by Paul Dirac, and sometimes it will be. So this set of three is called a spectral triple. Actually, there are two other, spectral triple is actually a quintuple. There are two other elements that are very important and will make their entrance shortly today or tomorrow. Okay, so the Dirac operator enables to describe in purely algebraic operator terms the usual structure of geometry. So since the description is algebraic, it will be easy to generalize to the non-commutative case, and now I will have really a non-commutative geometry. Before I was really talking of topology. So let me say, for example, if I have D, I can define a distance, and so a metric structure, over the space of states, pure or not. And this is the distance. I take two states. The states are maps over the elements of the algebra. So this is a difference of two complex numbers. Take their modulus. And I take the supremum over all elements such that the norm of this is smaller than 1. See, this is an operator. And the commutator of this will be an operator of the Hilbert space, and this will have a norm. Okay,
But that is the semi-norm.
yeah, but this is with a norm. I can do it with a norm. Yeah.
What is about it real? Since algebra had a norm, right?
Yes.
So you can always use the metric induced by the norm. Why do you need this?
To calculate what? This is
I mean,
This
on
is
the,
a-
on the algebra, I can define a metric induced by the
yes,
norm.
yes.
So
But
what
this is the metric. This is the metric which will give you the distance.
That one.
That one, no, because what you mean? So what is the distance? If I have two states, how can you define a distance? You can define a convergence. But you can.
What I mean is that if I have a norm,
Yes.
and if I have algebra is a vector space, it's a linear vector space.
Yes.
So norm of A
Yes.
minus
I want to see. Let me understand slightly better. You have these two states, phi 1. So I have these two. I have these two, phi 1 and phi 2. Okay. Now I want to know the distance between those two.
These are elements of the algebra, right?
No, they are states.
Duals of the algebra.
Yeah, so they're not elements of the algebra.
Okay.
The dual of a sister algebra is not isomorphic to the sister
No,
algebra.
sorry, but the dual forms an algebra or not?
No, I cannot multiply them.
Okay.
You don't multiply points. They are like that. So I cannot multiply them. They don't form an algebra. Instead, this is well defined.
Oh, so
It
this
gives-
is in the dual.
Yeah.
Yeah, it's something.
Yeah.
I mean, what you are saying is like as a dual space has a natural norm, dual norm. That's what people are asking, right? That something is dual, is functional.
Yeah.
So as a functional, they get the natural dual norm, which will be instead of the commutator is just norm k less than equal to. That's what you are asking, right?
I was asking a more trivial thing.
Ah.
I was asking that in a, if I have a space with a norm,
Right.
I can always define a metric there in inside. Doesn't
That
matter
is on
what
the
the
space.
not on the dual.
It is on the
So
dual
I'm saying
space.
if the space has a if the space has a
No,
Yeah,
it's
but
on
the space
dual.
of states
It's on the dual.
yeah, so the dual, if the dual doesn't have a norm, of course my statement is
No,
not.
but dual has a natural norm induced from the norm of the original space.
Yes.
But this is another semi.
This
This
is
is not the original norm. I mean,
So
the
what is
motivation will be clear. Motivation will be clear because this is actually modeling like if you think of pure state, this is restricted to the pure state and give you the distance, Riemannian distance.
Yes.
That's
This is
why
the
motivation.
this is the distance.
Next line is
Okay, and of course over the same set of points topologically, you can give lots of distances because you can have a measure. Okay, so in general we take the linear thing, and this would correspond to which Dirac operator, and in particular, this is an exercise, but it's not a difficult one. If you take the algebra of functions over the line, and then you take as Dirac operator more or less the one of Dirac, so the derivative, and it's possible to prove that the distance between x1 and x2 is exactly the modulus of x1 minus x2. Okay, but now if instead of taking this operator, I multiply this by any function of x positive, this is still a good Dirac operator, and it will still give me a good distance, but it will not be the linear distance. I will squash points. In fact, if I take a Gaussian here, I go to the finite distance over all the points. And now the original Dirac operator, gamma mu d mu, the one really introduced, knows a lot about the spin manifold. Okay, now notice one important thing. If I want to use Dirac operator, I have to go to spin manifolds, necessarily. But, and this would be another series of lectures by mathematicians, they actually do it. The Dirac operator knows a lot about the spin manifold because, you know, it knows about the metric in the sense of metric tensor. It knows about the distance, for example, like that. It is the square root of the Laplacian, so it knows everything that the Laplacian knows. It's shape of the drum, almost, and something. And the Dirac operator plays index theorem and everything. So the mathematicians like Atiyah who have done beautiful things with the Dirac operator, and they have not proven the Riemann hypothesis. They have done lots of things. So the Dirac operator is a powerful object.
So,
And
you have stated a formula for distance.
yes,
So it is acceptable because you have elegant points to pure state. So
Yes.
phi1 minus phi2 is acceptable.
yes.
But I don't understand why do you impose the condition d comma e has to be less than equal to 1. That's physically not understandable.
I'll tell you why. I will let me go a little bit ahead and solve this problem. Okay? So I want to have the line here, and I have 2 points on the line. Okay? And let me do it for real functions. The complex, the phases will not play an important role because of the modulus. Okay? Now I'm telling you that the distance is the maximum, the supremum, between all functions. So this is a function. The value of the difference of the value between these two. Okay? Now, over all, if I were to take over all possible functions, this number, so it will be the distance, so this is what I would call f1 of A minus f2, f1 of A of x1, sorry, let me call this x1, which would be like phi 1, and this is x2, which will be like phi 2, okay, the two states. So this is phi 1 of A minus phi 2 of A, okay? I'm taking real, so otherwise there will be a phase, but it doesn't. So and this is A, okay? This is the function A. Then I have to take the supremum. And so I can take another one which goes much faster between the two. And this will be a number. But now I'm imposing this condition. What is this condition? This condition tells me that the derivative of this function should be smaller than 1. Okay? Which means that at any point, the function cannot have a slope which is higher than 45 degrees. So I can take a function. Before it can do whatever it wants. As long, so how can I get the maximum? The maximum is that I can do, see, this is, the derivative must be everywhere bounded by 1. So I take a function of this kind, which before and after it can do anywhere it wants, as long as the radius is not larger than 45 degrees. Then between the two, I do it 45 degrees. This is clearly the maximum. Okay, so the phi 1 x1 of A minus x2 of A is exactly x1 minus x2. And this is granted by this condition. Okay? So if I don't have this condition, then all points will be at this infinite distance. And this because I was using the derivative. If I use a different function here, then I will have a different distance, which will not be translationally invariant. So this one, this is translation is a measure which is translationally invariant. Otherwise, I will have a different something different.
So how do you choose the Dirac operator? Is it a translational invariance?
No, not necessarily. Any physical problem will have its own Dirac operator. And we'll see that in the Dirac operator for the standard model, I will choose it in such a way that I will reproduce the masses of known fermions. So for the spectral model, the Dirac operator will be, and tomorrow we'll see it, will have to do with the masses, also with the masses of the things. So you don't choose the difference. Any problem will have, it's like the potential in a Schrödinger problem. No? So if I'm describing particles in a particular or fields in a particular situation, I will have the corresponding Dirac operator. For example, if I have a U1 connection, the Dirac operator, the covariant derivatives. Okay, and I am about to finish. Now, the presence of D enables an algebraic definition of one forms, because now everything has to be operators. Now, one forms have to do are very geometrical. No? One forms and vector fields have to do with the cotangent bundle, but I can do it. I define one form as the commutator with the Dirac operator. So this is a generic one form. So it's a spectral definition. It's an operator. Here there is a little bit of a technical difficulties because I have to implement the fact that d squared equals 0, and so I have to quotient out some junk form. It's a technicality which junk forms are heavy, so it's an heavy technicality, and I chicken out of it in explaining it. If you want to know it, I will describe it. So when you do two forms, you have to take away something. I will say something later on. The dimension of the space. If I am in all those concepts are well defined for usual manifolds, and I will find the results for the usual manifold. But I can generalize them to non-commutative spaces. So, what is the number of dimensions? If I have a manifold, I know it's in the definition, no? It's charts and everything, but I don't want to use points. So, I will do it with the Dirac operator, actually with the Laplacian, and this is due to Weil, so it predates Alencon and Gelfand. So, take this number of eigenvalues of the Laplacian smaller than a certain value omega, so this is a function of omega. It will be a ladder function, no? And take this limit, where d is an integer. Actually, it doesn't even have to be an integer, it can also be complex. But there will be a single value for which this quantity does not go to 0 to infinity, but only for a certain value of d, and this is the dimension. Okay, the growth of the eigenvalue of the Laplacian. That is well known. So if you are, it doesn't matter what Laplacian you take, because the number of dimensions is the infinitesimal. So it doesn't matter what Laplacian you take, the growth of eigenvalue will be fixed. And so this is a algebraic.
So it should converge to some constant value, non-zero constant.
Okay, you can look at this way and this way. I looked at it, this one converges to a constant value, yes. The constant value is irrelevant. The point is there is only one value for which this doesn't go to infinity or 0, okay, to a constant non-zero value. Then integrals. Integral is something else that you do with points, no? And but what is the integral is something that you have a function and you integrate, so you find a number out of the function. This is substituted by trace. A trace is a regularized sum of eigenvalues. We have to regularize, it's called the Dick-Smith trace. It will depend on the Dirac operator. It will depend on the Dirac operator because an integral depends on the measure. And as I was saying here, in the Dirac operator there is the measure of distance, so everything is there. And so there is a dictionary which is being built with all the concept of differential geometry, sorry, it's missing me, are translated in a purely algebraic way. And the dictionary, of course, now I've done the first elementary words of elementary school, dog, something, but everything, Poincaré duality, you name it. Basically, this is still being built. And in fact, K-theory is another important example. Now, there is algebraic and geometrical K-theory, so the things are captured, the set of projectors, which is an algebraic way, capture things. So, and all these concepts can be generalized to the case in which the algebra is non-commutative, because there will be states and traces and everything there. And manifolds. Manifolds play a central role, and so we need some requirement. And there are, okay, this one I prefer to do next time, because I want to do some of the exercises today. So tomorrow I will do this, but I will start by defining the manifolds. And the finishing of the lecture was, because you may wonder what this has to do with the Large Hadron Collider, because I'm doing pure mathematics, and tomorrow already I will show you how the standard model is a non-commutative geometry. And by using all these ingredients, I will then get to the Higgs and to get to the Large Hadron Collider. Okay, now I have 10 minutes, but I wanted to do some of the exercises because I asked some questions. So if there are other questions, however, this is a good moment to, as Kumar has done and our friend, you can interrupt me during the lectures. I don't mind. But if there are other questions, yes.
Yeah, the last slide.
The last slide I discussed.
Yeah.
Yes.
So you say that integrals can be substituted by trace.
Yes.
So now you haven't talked about non-commutative space itself. So if I do something on non-commutative space where xi, xt non-commutative, then the measures are also non-commutative. So can we lift them, the integrals to trace? Is it?
If I can represent my algebra as the algebra of bounded operators, and I have a Dirac operator, I can define an integral, and I can show you what the integral is since. So if I have an algebra, now this is, the proof of this is not linear, so I have an algebra, and I have a Dirac operator. Okay? Now, for the commutative case, I know what the integral is. So I know if I have a measure. So I can do the integral of dx of A over my space. Okay, and this is a number. Now to this, there will be a corresponding Dirac operator. Roughly, this is like the measure is the inverse of the Dirac operator. If the mathematicians close their eyes, it's like saying that dx is like dx to the minus 1. Okay? Don't quote me that I don't ever say that I did it among friends, but you know, it's this kind of thing. No, so if you have a measure at dx, then I can define derivatives in a semi-natural way, okay? So if I have a measure, to this measure will correspond one or more than one Dirac operator, okay? Now, I define the Dix-Meer trace, and this is the trace of Dix-Meer of d to the minus 1 times A, and the Dix-Meer trace is defined like that. This is an operator, okay?
That's omega.
It's the symbol for saying that this is a Dix-Meer trace. It's just conventional. It's not a quantity. So the trace, you know what it is. Is the sum of the modulus of this, the positive part of the variable. You know what the trace is. The trace is the sum of the eigenvalues. Okay, but this will diverge always. In general, because this is unbounded, so very likely that this will diverge. Now, instead, I define you the regularized trace, and the symbol means that it's a regularized trace. So, what is the trace? The trace is the sum over n of the eigenvalue lambda n. Okay? And the trace would have this which goes from 1 or 0 to infinity. Now, instead, I stop at a finite value, okay? I divide by the log of n, and then I take the limit of n going to infinity. Okay? So this is a trace which is regularized. It's not even obvious to show that this trace is cyclic. One of the properties of the trace, it has to be cyclic. You can prove that this trace is cyclic. Okay? And now, in this construction, this equals to the integral of A with this measure. Okay, so it's a regularized trace. Now, again, can you find for any algebra a good Dixmuir trace with a good Dirac operator? There will be one, whether it's the one that you look for is not necessarily true. For example, one good example is Kappa-Minkowski. The Kappa-Minkowski non-commutative space, I will discuss in my seminar, but is one non-commutative space, has difficulties in finding an integral which is also a trace. And there is not a good way of finding a Dirac operator as a fully satisfactory way. So this is well defined, but this doesn't mean that you always find the result. But if you have a Dirac operator with all the properties, and if this is a C-star algebra, this is well defined. It doesn't converge for all elements, like the integral. So not the integral of every function, continuous function over a compact manifold is finite. There are integrable functions, and also there will be integrable elements for which we define. But if I don't regularize, then basically everything will diverge.
So suppose A is something like a trace class operator.
Then it's zero.
Then it's zero.
Then it's zero. Because this Dixmuir trace captures the behavior at infinity. The trace class operator at infinity goes too fast to zero. So the operator which is gives you a finite is 1 upon n. The compact operator, the inverse of the number operator. Okay? And then this gives you 1, because it's or probably Mascheroni, but it gives you a finite. No, it gives you 1 exactly. So in this case, but so because I don't want a trace class operator is too well behaved. Instead, I want to capture the behavior at infinity. So. Okay, I don't know what to do.
Just a small question. You talked about this dimension coming from the growth of the eigenvalue.
Yes.
Does that work for Lorentzian manifolds or only for
No.
utility?
No. I will be Euclidean probably until the end, because I won't get to the Lorentzian thing. If you want to do Lorentzian, I have to trace back to the beginning, and instead of talking of Hilbert space, I would have to talk about Krein spaces and do all structures. So things have been done. There isn't a complete solution. Then there are even weak rotation. So the Lorentzian problem is probably the important thing. In fact, next week there is basically almost one day on the Lorentzian thing. So now this is it's the last lectures, if I get there, is about Lorentzian. So is the thing to understand. Everything here is Euclidean. Unashamedly, I'm sorry. As a physicist, I'm always a little bit ashamed, but thanks to Toft, we can do lots of things with Euclidean, and let me.
And the other thing is, can you handle boundaries?
Yes, boundaries are no problem. No, a boundary are actually better. So if you are on a compact with boundary, things are actually better and very nice, and so no boundaries instead are no problems. And in fact, I can, if I don't have a boundary, and I am in R4, and I take the Dirac operator,
No,
Then-
we're talking about compact any.
Okay, yes. No, but to do physics, I have to somehow put always an infrared cutoff,
Okay.
which is not a big problem. Otherwise, the spectrum is not discrete.
Right.
And when the spectrum is not discrete, I can still do things, but I'll have to talk about spectral densities. So the infrared is, but in physics in general, putting infrared cutoffs is not, is a mild regularization. Then if you have near a black hole things, but in general, we grew up thinking that, okay, infrared is not a problem, it's ultraviolet the big problem. Then now we're learning that also infrared, because of information, etc. We go backwards instead of going forwards. But in any case, it's for quantum field theory, for this kind of standard model, it's not the infrared the problem. It's the ultraviolet. And I will not put black holes in the game in information theory. So infrared. How much more do I have? Because I can.
Enough time is
Enough time, okay. Where is the pen drive? Okay, exercises. And okay.